Bon dia a tots, benvinguts al SIMBa. Avui tenim un dels nostres organitzadors des de fa ja un temps, que és el Pau Mir, que és el nostre organitzador a l'UPC. I res, dic que avui donarà una xerrada, acaba de tornar de la visita, i la seva xerrada serà Classification of Symplectic toric manifolds.
So I will talk in English, basically because I have the material in English and this will be in Catalan, but let's do it in English. It will be recorded and available on the YouTube of SIMBa. And today I want to explain a bit how it goes, the classification of a special family of manifolds in differential geometry, which is a family of symplectic toric manifolds. So it's a family of manifolds which includes some examples which are really used in physics and in dynamics, which basically has two properties, which is symplectic, and toric. We will see in detail which are these properties, and after this, we'll see the definitions and some examples of this kind of manifolds. We will see which the tools we use to classify, which are the tools that we can use that are intrinsic to these manifolds, and we will see that we can pass from the differential geometry structure of these manifolds to some really basic and simple combinatorial invariants, which will allow us to classify this. So we will pass essentially from manifolds, which are higher dimensional, to polytopes, which are something that we can really study, and there's a lot of theory of convex polytopes that will allow us to talk about the regional. So we will pass from geometry to combinatorial to algebra combinatorial. We will pass from manifolds to polytopes. And we will see the two big theorems in this field, which first said that, okay, for each manifold there's a polytope, and then the biggest one will say also for each polytope, a specific class of polytopes, there is a symplectic value. But there's a relation, a one-to-one relation, which is a complete classification of this kind. So I have 40 minutes. I will try to explain what I want to. I won't enter into the details of this classification because there's a theorem that has to be proven in order to say, okay, this is a complete classification, but even I don't need the proof. Although I don't need the proof, I think the idea will be like really. So let's try and we can do everything out. So let's start by talking about symplectic toric manifolds. So first of all, symplectic manifolds are the big class here. So symplectic manifolds are field of study by itself. There's a category in archive, it's symplectic geometry. So this is a very big class of manifolds, but nevertheless, already in the definition, there's some conditions that not all manifolds can satisfy, and that the first time you see, you can think that are quite specific and quite restricted. So what's a symplectic manifold? It's a manifold that has to be, first of all, two-dimensional, and this is in order that the structure that we're going to put on it has to satisfy two conditions. So it has to be something which is two-dimensional and paired with some two differential form, which has some conditions. So it's a manifold. This means that it's dimension 2n, so even dimensional, and omega is a two form. So let me say that this symplectic manifold is the pair of a smooth manifold, a classical smooth manifold, is this n, and a differential to form which is what we call normally omega, which has to have two properties. So closed, meaning that its differential is 0, and also non-degenerate, which is maybe a bit tricky condition. Non-degenerate. That can be stated in many ways, but one of them, which is easy to write, is that it always satisfies that if we contract this form with two vector fields, and this is 0 for any we put in the first place. This means that the second one was 0. If this happens, so if this implication is true for any combination here, then we call omega non-degenerate. This, in other words, we'll see later, is another way to say that for any function that we have in this manifold, for any smooth function, we have a unique vector field that contracted with this omega is equal to the differential of this function. This is the Hamilton's equation if you want, but this is the shorter way maybe to say the same, that the form is non-degenerate. So this is a symplectic manifold, or a manifold that needs a structure like this is a symplectic manifold. And there are many examples of symplectic manifolds. Just to give you, I will move now to the second. Let me, sorry, which is, can you tell me which? So, some examples, just, I think that here in the audience, most of you have seen symplectic manifolds, but just for someone that never saw symplectic manifold, the most natural manifold we can consider are symplectic manifolds. So even dimensionally clear spaces are symplectic manifolds. So one of the most important examples is R2n. This is a symplectic manifold, and we can equip it with a lot of symplectic structures. One of them, the most natural one, is this. Dx wedge dy. If we use coordinates x and y from 1 to n for the x and for the y's, this is a two form. So sorry, I should have. Yes, it's. But this is a two form which is non-degenerate and which is closed. Basically, if you do all the computations, you can see it, but it's the canonical form of differential two form, which is simple. Another example is, in general, any oriented surface. We call this big sigma by sigma any oriented surface. And if we equip it with an area form, this is a symplectic manifold. So what happens in an oriented surface? That an area form is a Morgan form, is a well-defined form. And in this case, it's closed and non-degenerate. So for any oriented surface, we can find a full family of symplectic forms, which is essentially all the area forms we can put on it. There are more examples, but let me just add another one, which is important for what is coming after this, which is the cotangent bundle of a smooth manifold. So if we call G star n the cotangent bundle of a smooth manifold n, which automatically is even dimensional. So m can be n dimensional or any dimension, but then the cotangent bundle is even dimensional. We can equip it with some form, which is the natural pairing of the coordinates in the base and the conjugate coordinates in the fiber. And you will see that it's really similar to this one, because by Darboux theorem, some classical theorem in symplectic geometry, these always have this, where the q's are the coordinates in the base and the p's are the coordinates in the fibers. So symplectic manifolds are something which is used a lot, and I will talk a bit about why here. But essentially, the motivation comes. The motivation comes from classical mechanics, because in classical mechanics, the natural setting is that you have some quantities that you know from physics that are conserved, and then you know to compute trajectories of particles in this system. Particles that have some conserved quantities. It can be energy, it can be momentum, it can be anything. One way to formalize this, which also takes into account that the two main variables which can be free in this system are position and velocity, is symplectic geometry, because symplectic geometry has this natural pairing of coordinates, of variables of directions, which for us can be position and momentum in this direction. Also, symplectic geometry, together with Hamiltonian dynamics, are the tool that allows us to formalize and to formulate this motion in which some quantities are concerned. So basically, the origin of symplectic mechanics, symplectic geometry, and the motivation is symplectic mechanics. So let me just in this sense, sorry, so let me just write that for a given function that I call h, for a given small function defined on a symplectic manifold, omega induces a vector field. This is the key point of the symplectic structure, which is that we throw a function into a manifold, and then this omega induces a vector field, which we call hamiltonian vector field. And we call them this way, via this equation, which is unique. It is unique vector field, sorry, which is defined via this equation, the contraction of this vector field with omega being minus the differential of it. And this pairing of function and vector field is what is essentially the magic of this setting, because okay, not for any vector field there's a Hamiltonian. This function is called a Hamiltonian for this vector field if it exists, but for any Hamiltonian, for any small function, there's a vector. And what's the magic of this vector field? We can compute its flow, and the flow of this vector field is the trajectory of the particle of the system, if you want. And the flow of this vector field preserves h, which is essential. So if you're a particle that moves along the flow lines of the Hamiltonian vector field of h, the quantity h will be the same during all the trajectory. And also, the symplectic form will not change from this trajectory, which is also important because the structure of the manifold has to be the same along the trajectory. So essentially, this is a big motivation for studying symplectic manifolds, in which we want to put functions that then we can, in some sense, pair with the symplectic form, pair with the symplectic form to give a vector field. And we are going to be focused today on symplectic manifolds which admit toric action. So the second part of the definition of the class of manifolds that I'm talking about today is that they are toric, not only symplectic, but symplectic and toric. And what does it mean? That we have some group acting on this manifold, which is a torus, and a torus of maximal dimension. So if we are working with a manifold in dimension 2n, we want that this manifold admits an action of a torus dimension n, which is a maximal one, by the way. So yeah, let me maybe already define what's a symplectic toric manifold. But essentially, what I will write here is that a symplectic toric manifold is a symplectic manifold which admits toric action, but there's more. This toric action generates a vector field, induces a vector field on this manifold, for which there is a function that satisfies this equation. Because it could be, okay, we have an action, it has a vector field, but we cannot find any function that satisfies the equation with this vector field. But for our case, we will require that this function exists, and this function is called moment map. So we need that the action of our torus in the manifold, for this action exists a moment. If there's a moment map for this action, we call it a symplectic toric. So basically, let me write all of this, but just for completeness, because if I'm talking about symplectic toric manifolds, at some point, I should write this. You will see that there's more conditions, because you will see that I add the conditions of connectedness and compactness. There's some authors that don't add the condition of compactness, but for the result, it's necessary to consider compactness. So in the definition, toric manifolds, symplectic toric manifolds, sometimes people don't require compactness, but for the result is valid, as I will state it, for compact manifolds. So I will already put this condition in the definition, and a lot of people also do it. So a symplectic toric manifold which is made of this group of elements, instead of this set of elements. You will see that it's a symplectic manifold, what we had until now, with the action of a torus of dimension half of the manifold and some function mu, which is a moment map of this action. So this is a connected symplectic toric manifold. It's a connected and compact symplectic manifold. With an action which is effective and Hamiltonian. So an effective Hamiltonian action, and recall that effective means that the only element that acts trivially is the identity element. And Hamiltonian means that there exists a moment. So basically, I will write this now as so that an effective and Hamiltonian action. Of a very specific group, which is the torus dimension. So, what does it mean? The key part here is that this action is effective and Hamiltonian, and effective means that the only element of the group that doesn't move anything is the neutral element, the identity of the torus. And Hamiltonian means that there exists a moment map for this action. So let me define Hamiltonian. In this case, in this very specific case, so in general, Hamiltonian will mean something more general that involves the group. But since now I'm working in this case with toric actions, I will already consider that the Lie algebra, this group is isomorphic to Rn. So I will give a definition which is only valid in this case for actions of the torus. For actions of other groups, you will need to see a more general definition of Hamiltonian than the one I'm going to write here. But for us, Hamiltonian means that there exists some function that goes from n to Rn called moment map. Which satisfies the problem. That's that. Now let me write the equation that you saw before. The contraction of this vector field of the action alpha. So let me add that the name of this action is alpha. And since it's an action of a torus, it can be decomposed into actions of S1. So this is like 1 times. We can look at each component of this action since it's made of n S1s. So for each component of this action, which I call by the subindex I, this contraction gives us the differential of mu I. If there's a function that satisfies this for this group action of the torus, we say that this is a moment map, mu is a moment map, and we say that the action is Hamiltonian. So we will work just with manifolds that admit Hamiltonian effective toric. Now we just arrived to the point, but before talking about the specification, let's look at some examples of these manifolds of symplectic toric. So you would think that this is very restrictive, or you would think that this is still allowing for a lot of manifolds. I don't know, what do you think? If it's the first time you see this definition, maybe not that you don't have any example in mind. Do you have any example in mind of a manifold that satisfies this condition of a symplectic toric manifold? Let me add Rn times Tn acting on Rn, or Rn acting. Yeah, the thing is that we are already considering compact symplectic manifolds. So this is really restrictive because Rn is not compact. So it's true that this is already a definition that does not allow for a very wide class of manifolds. The good thing about what I'm going to talk today is that you, at the end of the talk, you will have an idea of how big, which are the possibilities of this family of manifolds. So what can be essentially symplectic toric manifold? Why? Because we will have the other notion, we will have the polytopes, and we will see that for each polytope we have a manifold. So essentially we have which are the possibilities for symplectic manifold, we will look at them all. So before going to the classification, let me add two examples here. So two examples, just to visualize that this is a common class of manifolds, so this is not a super strange class of manifold. One of these, so the first one would be sphere. So one example is the sphere with the area form, which in polar coordinates, in cylindrical coordinates, is like this. And which is the action that corresponds here. So it has to be the action of the torus of half the dimension. So essentially one, and with some moment that I will not write because I want that it appears like naturally, but which is the action that we want to consider of the torus of the sphere. So the torus of one dimension of the sphere of dimension 2. An action that is very natural to consider is the rotation by the circle. So the rotation about the North Pole, sorry, about the vertical axis, is the rotation by S1. And if we use these coordinates, a moment map for this action can be the following. You agree that a moment map for this action should go from S2 to R, and is the following. So if we take an element zeta, theta, and this will do that, this is the moment. Why? When we check it, yes, really easy. It's really easy to check it. So if we contract the Hamiltonian vector field of this action, which is the Hamiltonian vector field of this action. So this action, rotation, generates a vector field that moves everything around the vertical axis. And if we write this in these coordinates, the vector field that should go here is the. And if we contract dv theta, I'm going now to see that this moment map satisfies this equation. So this is a proper moment. This contracted with the form is exactly minus dz. So it's exactly minus d. So this is satisfied. This is a really easy example in which this condition, in which we contracted the vector field with the symplectic form, we obtain minus the differential of the moment map is satisfied. So the sphere with this action rotation is a symplectic toric. And there are more examples, but just to, so the product of the spheres, as you can imagine, so if we take the product of spheres and we consider the rotation on each component of the product, we will also have a symplectic toric manifold. But another class of manifolds which admit toric actions are complex projective spaces. This would be the other main class of examples, which is CPN. In CPN, with the Fubini study symplectic form, which I will not write, but it's in complex coordinates, we can let Pn act on CPN, which is, since it's complex dimension, it has dimension 2n. So Pn can act as a maximal, torus of maximal dimension, and with moment map is, I will write, with moment map equal to 1/2 of the modulus of each coordinate divided by the modulus of all the components squared and sum. So this would be the moment map of the action of CPN. This is compact. This is a complex manifold which is compact, and there's a Hamiltonian toric action which has this moment. So essentially, these are the two basic families that can be defined in the most easy way that are symplectic toric. And now we will see how is it possible that we can classify these manifolds with this very simple idea of looking at a point.
Sorry, can I make a silly question? What fails with the cylinder? If you take a cylinder
So an infinite cylinder, you mean, or no? So if you take a finite cylinder, with first problem that you have is that it's not a smooth manifold. So you have some corners in the cylinder. This can be already a problem. So in this setting, we're already supposing that the manifold is smooth. We don't have corners, we don't have boundaries.
And the case of Sn, it is also
No, the case of Sn is not because not all SNs are symplectic. And yeah, I think that now I don't want to say it wrong, but the only symplectic Sn is S2. No, maybe you can correct it. I think it's topology. Yeah, by topology. So you need that H2 of Sn is not zero, but for other S, for S4, for S6, you have topological conditions that make it not symplectic. So they get on symplectic structures. So essentially we have products of S2s, and complex projective spaces. But where's the polytope here? So I already spoiled that I will do the classification via polytopes, but we only have these elements in a symplectic element. So the polytope you will see it now is in the image of the moment. And we will see why. Because in this example already we can see that the image of the moment map, which let's compute it. Now which is the image of this moment. If we compute the image of mu and we want to draw it in R, we see that this takes values between -1 and 1. If we parameterize the sphere, we imagine that the sphere, this is the vertical axis of the Euclidean plane with 3 dimensions, and this is the z-axis. This is parameterized from -1 to 1 in standard parameterization. So the image of the moment map takes values from -1. So here it's -1, here it's -0.5, 0, 0.5, 1. It takes values from -1 to 1. And even more, which are the fixed points of this action? The points that don't move by the action are the poles. So the points whose image is the vertices of this image, of this polytope. In this case, this is a polytope which is very, very simple. It's already a polytope in one dimension. But in a more general case, for instance, in CP2, if I do the subcase CP2, we take G2 acting on it, and this is just, this would be 1/2 Z1 squared over Z, and Z2 squared over Z. Which is the image now? This is more explicit because which is the image of this moment map? Well, Z2 squared is just the sum of all the components. So in this case, it will be 0, Z0 squared plus Z1 squared plus Z2 squared. Maybe I'm going to pass here because I'm assuming that you are a bit familiar with complex projective spaces, and I don't know if all of you are, but essentially a complex projective space is a quotient of the complex space of one more dimension instead of the 0 by a relation which says that 2 points are the same if we can multiply one of them by a complex number, we get the other. So it's the real complex space, or like the real projective space, but in complex. So essentially, the coordinate we use in the complex plane, like this one, the coordinates are Z0, Z1, Z2. But since it's the projective manifold, they are homogeneous coordinates, meaning that if we can get from a point to another one by multiplying by a number, they are the same. So when I mean modulus of Z squared, I mean this sum. And you see that if we try now, I don't say that this is super straightforward, but if we try to draw the moment map of this action, which goes to R2, it has 2 components, what do we obtain? So this can take only positive values. This is clear. This will be lower than this. This is clear, and this also will be lower than this. So, which is a maximum value? So this is a positive thing that is bounded by 1. This is a positive thing that is bounded by 1. So both of them are bounded by 1/2. And the equality can be made by the point, in this case 0, 1, 0. So if z is 0, 1, 0, this is 1 and this is 0. And this is the only point where the equality is realized. So the 0, 1, 0 corresponds to the 1/2 0. So the 0, 1, 0 goes here. And the other point that, well, there's another point which is a 0, 0, 1, which has as an image 1/2. This is 1/2. 1/2. Also, what happens with the 0, 0, 0? It goes to the 0, 0. It goes to the origin in this plane. But more importantly, we know that, well, maybe it's not clear at all, but the region of points to which we can arrive with this moment is this, because, or as I said, we have only positive values and are bounded by 1/2, and you put that, okay, why exactly this? Okay, so we compute things, we started computing, we will see that it happens this way. And what's more important here is that these points that corresponded to the 1, 0, 0, this went to the 0, 0, made a one. Then the 0, 1, 0 goes to 1/2 0, and the 0, 0, 1 goes to 0, 1. These are precisely the fixed points of this action. So if we compute this action of rotation, we rotate this. Well, I didn't write the action, so it's really complicated that we see it. But if we consider an action of rotation of this plane, the fixed points correspond to the points that went to the vertices of this. And the theorem that states it like properly and in formal way is the Guillemin at the Stemmer theorem, at the Stemmer, that essentially said that the image of the moment map is always a convex polygon. And this is the first very big theorem in this field, which says that it always happens that the image of the moment map will be a convex polygon, which at first glance is not evident, and the proof is some pages in the original paper. But it's a very, very strong result, which makes things easier because the theory of polytopes, as I said, it's really well known. It's a direct theory that there's a lot of books about it, and was already very well known when this result was discovered. So this is a result, let me write it here, from the 82 by a Guillemin Stemmer. Which says that essentially, in a symplectic toric manifold, and omega G mu, the level sets of mu are connected. What does it mean? If we look at the pictures here, it means that the level set of this point is connected, of course, because it's a point, but also the level set of any point here is connected. And this is true in general. And the other very important thing is that the image of mu is the convex hull of the fixed point of the action. What does it mean? It means that this is the image of mu will always be a polytope, which as vertices will have the fixed point of the action, and this polytope will be the complex region enclosed by these vertices. And this is called convex hull. So the image of mu is always the convex hull of the fixed points of the toric. And you would think, okay, this is really a very impressive result. And this image, since it's a convex spool of some points, will always be a polytope, and the name of its name will be. This is called moment polytopes. It's called moment polytope because it's a polytope corresponding to the moment map. But this is a moment polytope. The natural thing now, if we wanted to classify a symplectic manifold, is okay. We know that to each symplectic manifold it corresponds a moment polytope. Let's try to find if to each polytope in general in the space Rn we have a corresponding symplectic toric. And there's a work of the next big result in this work. There's a lot of work that try to obtain this, which is essentially a complete classification. And the big result comes from 8 years later from the Sun, which is still alive, by the way, which says that yes, there's for each polytope there's a symplectic toric manifold if the polytope is of some particular shape. So there's a family of polytopes to which we can find symplectic toric manifold, and this is the complete classification. So now, in the last 5-7 minutes, I will talk about the final this delta theorem, which is telling us that there's a class of polytopes for which we can find symplectic toric manifolds, and essentially, if two manifolds also have the same polytope, they are the same manifold, which tells us that the classification is complete. So the Delta theorem says, well, I already said more specifically, but to talk about the Delta theorem, we need to define which is this class of polytopes for which there are symplectic toric manifolds, which are delta polytopes. So now let's define a delta polytope. So a convex polytope that I will call delta in N is a delta polytope if the following happens. So if three conditions are satisfied, not every polytope is a polytope, but only the polytopes that satisfy a condition called simplicity. So if it is simple, or this is for the people in the internet, this is the definition that I want to explain now, is that this polytope has to satisfy simplicity, which means that at each vertex of the polytope we have n edges. We are in Rn, and we want that at each vertex we have n edges meeting. It could be more, so we could have that at each vertex we have more than n edges meeting, but we need that there's only n at each vertex. So this is n edges meeting. At its vertex. Then we need that it's rational, which means essentially that at each vertex we can consider the edges, which are like arrows in the space, and the coordinates of these arrows have to be rational, which means that all of them, if we multiply by some number, can be made integers. If we multiply this vector by some number, we can make all the coordinates integers. So it has to be essentially edges are of this form, the edges are of the form point of the vertex plus some number multiplied by a vector which is in set n. So we are using n, and it can be anything. This is the smooth, sorry, the rational condition, and there's a third condition, which is the smoothness, which is even stronger than this one. This is already a bit strong, but this one is really strong. This will say that at each vertex we have n edges meeting, and all of them can be made integer. We also need, this is a third condition, that with all of them we can make a basis of Zn. This is not general at all. So we need that, for instance, if we will see an example of this in the last meeting, but essentially is that at each vertex the VIs form a basis of the integer lengths. And now, what the Delta theorem says is that to each polytope of this class, we have a symplectic toric manifold. And the image of every symplectic toric manifold is a polytope of this family. And if two of them have the same image, have the same polytope, they are the same. This is essentially the big result. And well, since I started them some minutes late, I will end my talk with examples of these polytopes and examples of numbers. So I will end my talk here with some pictures, which essentially illustrate which are the manifolds for which that symplectic toric manifold and for which we have valid polytopes. So for instance, examples. We already saw one. Now in R2, well, in R is the one we saw in R is the line. Sorry, the second in the line. This is the polytope which satisfies all the conditions, and which is the original manifold behind it. It's S2 with the action of rotation. I will not specify the action, but it's the action of rotation here. This is the delta polytope. It has one vertex meeting, sorry, one edge meeting at its vertex. So we can use any coordinates here and we will satisfy all the conditions. So for instance, if we use, and this is the 0 and this is the 1, and this is the minus 1, this is the 1, this is such. In R2, what can we have? We can have, for instance, the example that we saw before, the isosceles triangle, an isosceles bitriangle. Which corresponds to CBT. But we can also have, for instance, what can we have? The square. And what's the square? The square is S2 times S2. And we can have more complicated things like that are called Hirzebruch surfaces. For instance, this one. And this is an isosceles triangle, and this is a square. But the polytope will be this one. This is also a proper polytope. Because at each point, this is clear. Let me put coordinates. This is the 0, 0. This is the 2, 0. This is the 1, 1. This is the 0. There's a theorem, there's a manifold, which is symplectic toric, which has this as the image of a moment. But now, so in higher dimensions, you can find many other polytopes. But now let's see non-examples. Already in dimension 2, there are things which are clearly, well, not that clear, sorry. But let's see, in dimension 3, there are things that clearly are not, there's a polytope, which are, for instance, polytopes that don't have, that do not have an edges meeting at each point. So this will not be a proper delta polytope because in this vertex we have 4 edges meeting and we need 3. So this one would not be an example of a delta polytope. There's no symplectic manifold associated to this polytope, but there's more tricky examples of non-delta polytope. For instance, this triangle. Which satisfies the first 2 conditions. It's simple and rational. It's not smooth, so it's not a delta polytope. Why it's not smooth? Because if we look at here, and we look which is the basis that we have here, the basis we have here is made by 2 vectors. Vector -1 and 0, and the vector -1 and 2. With these 2 vectors, we cannot generate, for instance, this point. Point 0, 1 cannot be generated with these vectors with a combination of elements of Z. Other examples which at first seem that should be possible, but then, for instance, this one here, if we deform it a bit, so if we change a bit this one, for instance, if we consider this polytop, this is already a non-example. This is 2, this is 2. This is not. Why? For the same reason, like in this case. Here we have 2. And this vertex, the polytope is smooth, and this vertex, the polytope is smooth. And this vertex, the polytope is smooth, like here it's really smooth. But at this vertex, the polytope is not smooth. With these two vectors, we cannot generate this one. Thank you. Just to finish, this example is good because in this definition, we can choose B. So in this case, you would say, oh no, but you can make this bigger and smaller. Yes, but even if we make it, instead of taking the -2, 0, we take the -1, 0, we still cannot generate, for instance, this with these two vectors. So this is an example of another polygon. Just to add, why do we do this classification? Why is it so important? It's because now, from the information we have on the polygons, we can do many things. For instance, quantization. There's a lot of results in geometric quantization which explain how can we quantize and how can we do quantization simply looking at the polygon, looking at the integer points inside the polygon and looking at the volume of this polygon. So now we have a very massive tool which says that okay, you don't need to look at the differential manifold, you can look at the polygon, and the essential information is in the polygon. So you can do many things just looking at the polygon, which is a very simple tool. So that's all for today, and thank you.
So if there are some questions,
Yes, one question. From this last example, you should tell me that you can split. It is true that you can split all the possible polytopes that with a simple polytopes. I mean, this last one.
You mean like squares and triangles?
Yeah.
For instance. Okay. Yes. This last one looks like yes. We could think that this is like a mix of S2 times S2, which corresponds to the square, and CP2.
Yes.
And it has some relation, but there's another way of thinking about this, which is maybe more appropriate, which is that this polytope can be obtained by simply. So first of all, this polytope corresponds to a manifold, which is very similar to a manifold that could have this polytope. Do you agree? Well, maybe you don't agree, but you have to believe that if a symplectic manifold has this polytope, and another symplectic manifold has this polytope, which is also a Delta polytope, let's imagine that this part is isosceles and this is a Delta polytope. They are very similar. Essentially, they have 4 fixed points. The action is essentially the same in the edges. And now this is really similar to this. We can take the limit here and think that there has to be, we can deform this manifold. So this is like topologically the same manifold, symplectically the same manifold. But this one clearly are different because this has 3 fixed points and this has 4 fixed points. But the difference can be just taken at the limit. And in fact, what is done to know which is the surface corresponding to this is to think that we chop one thread. So we start with CP2, and there's something called blow up, symplectic blow up, that we apply at the vertex. So at the fixed point of the action in the original manifold, we locate a fixed point, and we do something here, which is essentially symplectic gluing. We take out this point and we replace it by a copy of CP. It's called a blow up, and in other branches of geometry it's also used, but in this case it's symplectic blow up, and we pass from there, in which we had a fixed point, to this other manifold which has 2 fixed points. So we blow up a polygon. We could do it at any vertex. So if we cut here, we obtain another polytope. But there, your question, there are manifolds which are not easy to write as a simple manifold, as a sphere, CP2. They are more complicated manifolds, and therefore usable surfaces.
Okay, the technique that you already told is that sometimes for the square you do the same but for two vertices. Two of them from the R1 to square.
From here to here. From here to here, what I do is I consider this manifold S2 times S2, and I consider a rotation action here. So I consider this manifold, which is made by two spheres. And one point in this manifold is a pair of a point here and a point here. And the action I consider here is the double rotation. Double rotation, it means with different, sorry, it's not the proper one. So a rotation in both components, but it doesn't have to be the rotation with the same angular velocity. So independent rotation. So then I will have, let's draw it. So which are the fixed points of this manifold? One fixed point is this pair. Another fixed point is this pair. Another fixed point is this pair. Another fixed point is this pair. These 4 points are the points that are not moved by the action and correspond to this. And which is the submanifold corresponding to a point here. We know that it's a connected subset of this manifold. It would be a manifold that, on the one hand, moves, but on the other hand, is not moving. I didn't tell this, but the edges on the polytope correspond to manifolds, to submanifolds here that don't move as the maximal direction possible. For instance, point here would correspond to a point here and this one. And point here would correspond to a point here that is rotating in this one, and is not rotating. And then in general point here is a point which rotates in both spheres. This idea here.
So the proof is constructive, like
Yes.
there's an algorithm or something to build from it.
There's a complete algorithm that says, okay, give me a polytope, you give me this, and I know how to construct a symplectic manifold, which admits a toric action whose moment math has an image, this, exactly this one, and it's constructed. So in another talk, which would be like 1 hour and a half short talk, it's possible to explain. I could explain the construction, the whole construction in general. I can give you the idea. The idea is that you consider as a standard action of the rotation of Tn over Cn. So you consider Cn as the complex dimension n, and you consider the rotation action on each component. So you consider S1 rotating the first component of Cn, another S1 rotating the second component of Cn. And then you take this Cn with this action, and you take a quotient of this action, but not a normal quotient, but a symplectic quotient. You will reduce the dimension by 2 times the dimension of the group active here. And the group active would not be Tn, but a subgroup of Tn. And to find the subgroup of the Tn that you have to take to then the symplectic quotient, you have to look at the kernel of some map, which essentially takes the edges which are perpendicular to the faces of the polytope and send it to the canonical basis of Rn. This is a very beautiful construction. So the first time I saw this, it was amazing. And it's worth a ton. So at some point we can do it again. I will explain this construction very good.
That's your question. If you, in the manifold you have the group action.
Yes.
Is this a part of the correspondence? If you had 2 different toric actions with the same manifold, would it be the same?
This is a very good question. So if you consider another action of the same manifold, it's another symplectic toric manifold. Because when you talk about the symplectic toric manifold, you have already specified the action on the moment. But your question is very interesting because it means, okay, if I have a symplectic manifold and I can put there two different toric actions, do we obtain similar polytopes? And the answer is yes. Yes. So, but why? Because this is a bit constrained by the fact that we are not considering general toric actions, but maximal toric actions. So we are always considering torus of maximal dimension. And essentially all of them are quite, you could say like they're quite subjective.
This is a characterization of symplectic toric manifolds up to
symplectomorphism and equivariancy. So, and this is also a very good question. But they say, okay, they are equivalent. But what means in this context equivalent? Equivalent means that if 2 manifolds have the same polytope, they are symplectically equivalent, meaning that there is symplectomorphism, which is continuous and smooth and with continuous inverse map, which preserves the symplectic form. So which difference the pullback of the symplectic form in this map is the same symplectic form in this symplectic form in the other. And equivariancy means that if we make the group act on this manifold, before or after, we still have the polygons.
So in this case, it will have the same. In this case,
Yes.
Yes.
Well, no, not really.
no, up to something.
Up to it. And this is very important. Up to, because I didn't talk about it, up to and a fine transformation.
Okay.
This will be like more, this will need a bit more of explanation, but it's up to a fine transformation.